Greetings. It's a great pleasure to be with you today. I'd like to thank Professor Lin Lu for the very kind invitation. I'm sorry that I cannot be in Beijing in person. We know the situation in the world today. And also, I'll be traveling exactly at the time of the lecture, so I have to record this via video. But it's a great pleasure to be here, and thank you again, Professor Lin Lu. Today I'll be talking about a new concept that I've been developing, which is called feast or famine. And that explains how we go from the reaction of flight or fight in general adaptation to a new concept for chronic stress and a substrate for its clinical manifestations. So this is where I live and work, Syracuse, New York, our trademark building downtown, and the university just above me, the medical school and the hospital. In this slide, I'd like to share my conflict of interest, which is required now, but I'm not receiving any money from external companies. So you don't have to worry about commercial bias here. And this is our research team and collaborators, both at the State University of New York in Syracuse, and other places where we've worked and places that we have collaborated with, including Chongqing Medical University in China. So the rapper Immortal Technique says that life is war and every day is a battle to me. So life has big fights, and we have evolved over generations and millennia to deal with those. We are evolutionarily prepared to deal with predators, and you can see here a very dangerous predator. I'm sorry that if we met this predator in an open field in a savanna or not in the zoo, but like in the forest, we would immediately have a very severe stress reaction. So that's the predator. And how do we handle the predator? So the predator looks at you and you look back. And there is an impasse. Then there is a confrontation with only two possible outcomes, which are called flight or fight. Flight, the predator pursues you and you run away. So it's a flight, you're flying away from the predator. And then eventually the predator may catch you and the predator eats you. Or you may run faster than the predator and you may get away. But this is the most logical outcome for the predator, at least. And then the second option is that instead of running away from the predator, you can go and fight the predator. And you would not imagine that, like these gazelles from Africa, would be very courageous and fight the predator there very well. So here's the gazelle again fighting the cheetah super aggressively. And you'd not imagine that a gazelle would be that aggressive against a cheetah, but in that stress of the moment, you can fight back. So how did this concept of flight or fight evolve? Walter Cannon was a pioneer physiologist of human emotions. And here are a few facts about him. He was born in 1871 in Wisconsin. He went to school in Wisconsin and Minnesota. Then he entered Harvard College in 1892. So exactly 130 years ago. He graduated summa cum laude, which is the highest you can graduate at, in 1896 and entered Harvard Medical School. He graduated Harvard Medical School in 1900 and was appointed instructor in physiology. And in 1906, so 6 years after he, graduated from medical school, he was the George Higginson Professor of Physiology and chair of the Harvard Department of Physiology. So Cannon introduced this physiological concept of flight or fight. So he was very attracted to the physiology of emotion, and he showed that when an animal is strongly aroused, like what you saw in the photos before, the sympathetic division of its autonomic nervous system combines with adrenaline to mobilize for an emergency response of flight or fight. So that's essentially the body on an emergency situation, you know. And the sympathetic-adrenal system orchestrates changes in the blood supply, sugar availability, the body's clotting capacity, and marshaling resources are keyed to give the individual what's called a violent display of energy. So all of your energy is mobilized really fast, and anything that's not relevant to confronting the predator is completely shut off, as you'll see now. So he summarized his findings in a book, Bodily Changes in Pain, Hunger, Fear, and Rage. And here are the flight or fight response. I'll go over this in more detail later, but you can see that the heart beats fast, your pupils dilate, you have palpitations, your breathing changes, you sweat, your whole body has like this emergency reaction. So this is organized in terms of the body by two effector arms. And there are multiple systems involved in stress. These are just the most classical and the most well-studied and the ones that were discovered first. So this is just like a historical background. So the autonomic nervous system, the sympathetic nervous system, which ends up releasing noradrenaline, which is made in the adrenal medulla. So the internal part of the adrenal gland, the adrenal medulla, makes adrenaline, which goes into the circulation. And simultaneously, the hypothalamus pituitary adrenal axis is activated, and you have the production of CRH in the hypothalamus, which stimulates the pituitary production of ACTH, which in turn circulates and stimulates the adrenal cortex to make cortisol. So the adrenal gland is really the stress gland. The medulla produces adrenaline, which is the internal part, and the external part, the cortex, makes cortisol. And then your blood is just floods with very high levels of those two hormones, and that really creates the body's emergency response. So this reaction begins, in terms of the brain, in the amygdala, which triggers a response in the hypothalamus. So it activates the pituitary gland to make ACTH. The adrenal gland medulla is activated simultaneously and makes epinephrine. ACTH results in the production of cortisol in the adrenal cortex, as I showed before, which does multiple things: increase blood pressure, blood sugar, and suppresses the immune system. So you'll see anything that's not really relevant to that acute stress response is suppressed. So when the lion is running towards you and you have to save your life, it's not relevant for the body to be trying to, address an immune problem, which has no immediate impact. The initial response and subsequent reactions are triggered in an effort to create a boost of energy. And the boost of energy is activated by epinephrine binding to liver cells and the subsequent production of glucose. In addition, the circulation of cortisol functions should turn fatty acids into available energy, which prepare muscles throughout the body for response. And the catecholamine hormones, such as adrenaline or noradrenaline, facilitate immediate physical reactions associated with the preparation for violent muscular action. So we are talking about a very profound physical reaction that's like an emergency signal. So you prepare for violent muscular action. There is acceleration of heart and lung function. You get pale or you flush. As I said, anything that's not immediately relevant is shut down. So the digestion slows down or stops. If you're running from the lion, the digestion is not your preoccupation. There is a general effect on the sphincters of the body. There is a constriction of blood vessels in many parts of the body, which elevates the blood pressure. There is a liberation of metabolic energy, sources both, as I showed before, fat and glycogen for muscular action. There is dilation of blood vessels. The tears are inhibited. The pupils are dilated. There is a relaxation of the bladder. Inhibition of erection. So when you are running from the predator, you don't need to be have an erect sexual organ and you're not going to have sex at that point. There is auditory exclusion, so you don't hear so well. Tunnel vision, you only see what's in front of you because you're trying to run away from the predator. There is a disinhibition of spinal reflexes, and finally shaking. So as you can see, that's the body's like very acute response to stress. And but what happens if the stress response keeps going? So a very famous and well recognized, but I think not as recognized as it should have been, Hungarian Canadian researcher called Janusz Hugo Bruno, his nickname was Hans Selye, described what he called a general adaptation syndrome, which was initially called Selye syndrome, and later he himself rebaptized it with the term stress response. So essentially, the word stress was used in physics, and he brought it to medicine, and we use it so much now, but he was the one who brought this word to medical use. And he describes this response as having three phases: an initial alarm phase that's followed by a stage of resistance or adaptation, and finally a stage of exhaustion and death. So here is he, and he published this, what he called the general adaptation syndrome, in a one-page paper in Nature in 1936. So he called it a syndrome produced by diverse noxious agents. So what he noticed is that if you kind of injure the animal, now we call it stress, but if you kind of affect the animal in a severe way by one mechanism, let's say by a chemical or by a physical mechanism or by a psychological mechanism, you end up, if you do that, in a strong enough way for multiple days, so no longer that kind of acute predatory stress that then the animal sees the predator and the stressor ends, but if the stressor stays there, the body eventually develops like a chronic reaction. That's the same reaction regardless of the cause. So he showed, and he understood that to be a response not to that specific agent, but a general response to anything that was disturbing the organism. And that's what he called stress. And he was nominated for the Nobel Prize 10 times and never received it. But he did receive a stamp from the government of Canada. So stress, and here's cortisol. So in addition to discovering stress, he really discovered multiple effects of glucocorticoids, and he studied them extensively. So he created the name glucocorticoids. He made the first modern classification and named of these hormones, and he discovered that they had anti-inflammatory actions. And eventually, the Nobel Prize was given to the discovery of glucocorticoids, but the Nobel Committee gave it to the person who discovered the chemical structure, which was difficult to do in those days. So Selye had the concept, the factor, had the extract, but he didn't have the amino acid sequence. So what are the effects of chronic cortisol? So he showed that there was chronic cortisol production during continued stress. So as I said, there is effects on mood, gluconeogenesis in the liver, digestion is slowed down. There are effects on muscle and in the heart, and blood glucose is increased, blood pressure is increased, and then there are effects on the skin as well. So the effects of stress are pathogenic. So these are not things that are good for you, and they help the body create a very acute emergency response to deal with a very immediate threat, but it's not what's kind of a good for your body to live a long and healthy life. So you have high adrenaline, and Cannon, when he studied the fight or flight, which is the more acute response, he focused more on his work on noradrenaline, which was an adrenaline, which was basically what they could do in those days. Selye focused more on the high cortisol levels that you have during this more chronic stress. And then there is high heart rate, hypertension, poor digestion, decreased immunity, muscle tension, high glucose levels. And so this is all what I call pathogenic signaling. So if this happens like, continuously or outside of the context of a very acute reaction, it's really not good for you. So these are what I'm calling now, and I'm creating this concept of a stress-induced pathogenic signaling, was supposed to be acute. So you either fly from the predator successfully, in which case, let's say if the predator runs after you, and you saw the slides of the predator catching the animal, let's say if the animal runs faster and goes to some other place or jumps a ravine, and it will seek refuge and rest and reproduce, or the animal dies. So it's just not possible for the animal to be running from a predator. Like if you put a gazelle and there are like 20 lions and they keep running after the gazelle, at one point one of them is going to catch the gazelle. There's no way that it can escape like 10, 20 times, So you can do this a couple of times, and then you have to find a quiet place and rest and eat and then reproduce, etc. And or else you just die. So so stress was supposed to be acute. So this animal here, the gazelle, it's either going to die very quickly, or let's say if it just jumps very fast and runs, it's going to survive, but it's not going to be in the situation very long. The body cannot handle being in the situation very long. But we are all mammals, just like the gazelle, and today the stress is ongoing and chronic. The predator could be a boss, or could be a spouse, and you are with them for long hours every day. So imagine if this gazelle had to work or to be married to this cheetah. It would be a very difficult life. And that gazelle is many of us, or all of us at some point, So everybody has a boss. Everybody has a spouse. That sometimes can be complicated. So you go through life with chronic stress, and I'll show you there are multiple things that are just ongoing in modern society that can cause chronic stress. So if you think about the animal famine, if you have no food, that's a huge stress. And stress in general and famine stress used to alternate with good feeding periods, with overeating during those feeding periods, and then reproduction. So wild animals do not eat as they run from predators. So the way that our whole biology evolved is that there was a kind of quiet period, and you can see the gazelles here all, eating and being happy there. Then comes the predator, and they have this acute reaction. And then if they die, they die. If they don't die, they go to a quiet place and they run away. And then they reproduce and they have like a quiet time. So these kind of different states happen at different times. So you had a period of rest and peace and quiet. The animal ate, and then the animal reproduced, and then the animal dealt with the stress. So all these hormonal ensembles, these hormonal sets that prepare you for one situation or another, they happen separately. So the animal here is not having an acute stress response. The animal here is not reproducing and is not eating. So you had different times, you had a different set of biological response. And then the body would go from one situation and one kind of a set of hormones to another situation and a different set of hormones. And what I call the opposite of this fight and flight state is the feast state. So in that feast state, there is food availability, there are no immediate predators, there is good climate, and that's typically why animals migrate. So when it's very cold, the climate's bad, they move away to a warmer place. Then when that cold place gets warm, they migrate back. So they tend to live in a good climate. There is no pollution in nature. There is partner availability. You see they are in large groups, so they can find a partner. So during that state, there is sex and reproduction. In reproduction, there is some fat storage, so you create a fat reserve that when you need it, when there is no food, you can, depend on that. You can try different foodstuffs. As the animals migrate, they are exercising, and there is no artificial light. It's all natural. So if you look, I told you about the hormones involved in the big hormones involved in stress. For the feast state, there is a hormone that I've studied over 20 years that's called leptin. That I think leptin is not the only one, but has a major role. It's like the major switch in the feast state. So leptin is made by the fat, and the more fat you have, the more leptin you make. So if the animal is starving, is in a difficult situation, it doesn't have much leptin. Then as it eats and as you begin to gain weight, the body then makes more and more leptin. So we studied leptin for 25 years and looking at the endocrine effects of leptin. So we showed, first of all, that leptin levels are pulsatile and are exactly inverse to pituitary adrenal function. So there is an inverse relationship between leptin and the stress hormones. And so here, in green is leptin, and the blue is HGH, and the red is cortisol. So you can see that as leptin goes up, the stress hormones go down. And it's a very strong inverse mathematical relationship. It's p to the 10 to the minus 8. So that's highly significant. Then we studied the role of leptin in reproduction. So first I measured the levels of, here is leptin, this is LH, and this is estradiol. And there is a very critical time. These are young, healthy women between 18 to 26, 27 years of age. And we collected blood at the National Institutes of Health, NIH, every 7 minutes for 24 hours. So they stay in the hospital 3 days. The last day is the study day. They have an IV, and through the IV, we collect blood samples every 7 minutes for 24 hours. And then we measure different hormones. And those days, they were studied here in days 8 to 11 of the menstrual cycle, which is a very critical period, which is when ovulation is triggered. So you can see that as leptin rises at night, and I did this myself, a very detailed mathematical analysis, the nocturnal rise of leptin is temporarily correlated to the change of LH from high frequency, low amplitude pulsation here to in the day, and then at night it goes to high amplitude and low frequency. And this is what triggers ovulation. So earlier in the menstrual cycle, it would all be like this first part, then it's switching to this other rhythm, and it's this switch that triggers ovulation, and this switch happens when leptin goes up. And in the absence of leptin, let's say patients with anorexia nervosa, for example, people who are starving, if there is no leptin, there is no switch, and the woman doesn't ovulate. And the estradiol levels also change. The relationship here is estradiol is a little more complex. But this LH is what really triggers this change in LH rhythm, is what triggers ovulation, and the rise in leptin is required for that to happen. Then I identified in Turkey 4 patients who were leptin deficient. I identified 3 initially, then 1 later. And I brought them to the United States and studied them for about a year. So this is the result of the first 6 months. The patients were obese because they didn't have leptin. Leptin gives the brain, a satiety signal. So if you don't have a satiety signal, you keep eating. So you can see that the male patient is here, and there were 2 women, and these are the 2 nurses that helped us. So look at the male patient. After 1 year with leptin, the weight dropped dramatically. So the patients, because I told you that leptin triggers hormonal sexual maturation. Without leptin, there isn't such a thing. So this is the baseline. This is after 6 months of leptin. So this is they get a leptin injection and the levels go up. And you can see that LH levels are very low, and it's called the infantile pattern, and then they increase. Testosterone goes up significantly, and estradiol also goes up. So, so here's the man we actually measure here called cortisol. So you have leptin, LH, testosterone, and cortisol. And you can see testosterone goes up dramatically, and he underwent puberty. So you need leptin for sexual maturation, and then eventually for ovulation, and then reproduction. Then we did another piece of work that we studied TSH, and we showed that in the absence of leptin, the rhythms of TSH are very irregular, erratic. It's behind my picture here, but you can see that they're really off. And the patient that had the leptin deficiency had a brother who did not have the deficiency, was a wild type. So you can see that in the healthy brother, you have leptin levels that are normal, they go up at night, and then TSH levels mirror those of leptin very precisely. And in the absence of leptin, TSH is completely erratic. So leptin is required for the normal rhythms of TSH and the normal functioning of the thyroid axis. So the novel concept of the feast state is that leptin is a key feast state hormone, and leptin effects include increased energy expenditure, decreased food intake, decreased cortisol levels. And you can think it's paradoxical because you're talking about a feast, but I mean, after you eat a lot, at some point you have to stop eating. So the leptin kicks in once you have eaten a lot already. Then you have decreased cortisol levels, so it does the opposite of the stress reaction. It activates the immune system. Remember that I said that during the fight or flight, the immune response was suppressed because the body was focused on, the emergency response. Leptin does the opposite. It stimulates the immune system. It decreases insulin production, so it decreases insulin resistance. And it regulates bone, so it stimulates formation of new bone, higher bone density, and reduction in fracture risk, so it makes the bone stronger. And it, as I said, it promotes sexual maturation and ovulation. So I believe that leptin is a key endocrine regulator of the feast state. So as I said before, in nature, stress and famine alternated with the feast state. So if you starve the whole time, an animal eventually dies. Or if you're stressed the whole time, the animal eventually collapses and also dies. And Celia's animals that were chronically stressed, at some point they died. It was the third phase of the stress response. Was the initial, there was an acute reaction, then they seemed to be, managing okay. It was like the mid phase. And then at some point there was what he called exhaustion and death. So here is a death by chronic starvation, which is a form of stress. Here's the gazelle running from the cheetah. And so that's the acute situation, and then you alternate that. Let's say if this gazelle, the cheetah is the fastest running animal, but it gets exhausted very fast. So if the gazelle, can keep going, at some point it doesn't catch the cheetah doesn't catch it. At some point the cheetah is going to stop and the gazelle can run away. So let's say that, for argument's sake, that this gazelle ran away and then joined this group here. Then it's eating, it's trying to find a mate, and it will be reproducing, and then you have the baby here, and then you have the baby gazelle, and then you have the baby and the mother there. So, you don't see any predators here. These animals are not stressed. So you have this situation and alternates with this. So you go from one to the other. So in the wild, stress and feast do not overlap. So you have acute predator stress. Your hunger goes away when you have that flight or fight reaction that Cannon described. The search for food ends, and there is no eating whatsoever. If the gazelle is not going to be, stopping, running away from the cheetah to go and eat some grass. There's no eating. So that's the situation. This is the tiger running from a boar. I mean, the boar is running from the tiger. This boar here is not going to go and stop. Oh, this is very nice grass. I'm going to eat something here. There's no eating at all. And the fat reserves grow without predators. So you have low stress, low cortisol, high leptin, reproduction, raising of the young. And so you you can be in this situation or you can be in this situation, not in the two of them at the same time. And the same thing could be said about sex. In acute predator stress, there is no sex, so the animal is not going to stop. And this gazelle here is not going to stop and say, "Well, I found a nice mate and I'm going to have sex now." So there's no sex there. And but for us, when there is sex and chronic stress can overlap, and people even talk about the stress-sex connection. And so we have now a societal paradox in that we have it all simultaneously. So these were different hormonal responses to different distinct situations, and they did not overlap. So today we have acute stress that becomes chronic. Then food has become cheap and overabundant, and we actually have stress eating now. So we eat when we are stressed, and then the eating, you saw that leptin suppresses cortisol. So I think it's the body trying to suppress the stress hormones, but doesn't work very well. So you keep eating and you keep being stressed. And we live in a hypersexualized world. So what happens biologically, what happens to your body when you have it all at the same time? You have high cortisol, you have high sympathetic tone, high adrenaline, you have high dopamine. It's been shown recently that dopamine was thought of as a pleasure hormone, can also be a stress hormone. You have high leptin levels simultaneously. You have the immune system, which is supposed to be suppressed. At some point, it flares back up. It's now overriding the cortisol suppression. And then you have overweight and obesity. And you have sex hormones because we live in a sexualized, hypersexualized world. So these different hormonal responses, which are supposed to be happening at different portions of your life, now they all happen together. It's like boom, everything on. And then what happens? This is very interesting that this is a paper from the end of last year, November of 2021. So it's not even 1 year ago, very recent. And this was a large multi-ethnic study of atherosclerosis prospective in the US. And they showed something that I thought everybody kind of knew, but it's good to have it proven here. Showing that the stress, they collected 24-hour urine. So it really shows the production of what you're studying over 24-hour period, not 1 point blood level. So they look of norepinephrine, epinephrine, dopamine, and cortisol. And then they use 3 different types of models to see how elevation of these levels here affected cardiovascular outcomes, cardiac events. And you see that the models are like 1.5, for norepinephrine, depending on the model, 1.5, 1.9, 1.6. But so it's 50, 60% more risk of a cardiovascular event if you have norepinephrine high, epinephrine high, cortisol is 1.6. So all of these, they go up together. So it's like you're not going to have one high and the other below. So they tend all to be together. So they consistently show that if the stress response is chronically activated, you have more cardiac events, which I think we all it's very logical, but it's good that it's been proven. I'm surprised that it was proven only recently. So based on everything that I've told you, I've developed a novel and testable conceptual framework for the pathway that goes from stress, depression, and medical illness. And with obesity in the middle. So you have stress and the weight gain, depression, medical illness. And how does that happen? So I call it persistent pathogenic signaling, PPS. So it's a novel conceptual framework for mind and body interactions and disease susceptibility. So in the intermittent stress, which is what the animals have and what we are evolved to have, you have acute confrontations and stress-free periods. And then there's neuroendocrine transduction, and the body makes hormones and cytokines. And there is either the flight or fight in some situations, and in others there is the feast. In this slide, I'd like to show you how the stress response evolved as an acute event. So we had this acute confrontation stress that I talked to you before, that you had the flight or the fight. And that's what happened here. In this case, we have the flight. And then there is neuroendocrine transduction, in which neuroendocrine axes are activated. You have the corticotropin releasing hormone, which stimulates the hypothalamic pituitary adrenal axis. And then you have the sympathetic nervous system that when it is activated, the body makes norepinephrine and epinephrine. Then the body goes into survival mode. So you have, it goes into two modes, kind of shuts down everything else that's not relevant for survival, and then pushes the body towards this kind of a big, stress response. So reproduction, the animal is not going to be, running from the cheetah and then going to stop and then try to, reproduce. It's not going to become social. It's going to be in fear. It will be retain fluid, because it's not the time to go and urinate and throw your fluid away. Then you have decreased immunity. It does not need to be fighting, infection or dealing with the immune response at that point. So the body goes into survival mode. And then here you have, in between a stressful or famine periods, there were periods of plenty. So you had an alternation of those stressful periods with these periods here. So the feast or the stress-free periods, you have energy loading, reproductive potential, and that's what I was talking to you before. So these you have hormones and cytokines, including principally leptin, which is both a hormone and a cytokine. And there is healing, energy storage, reproduction, and caring of the young. So we evolved for intermittent pathogenic signaling, yet today we have persistent pathogenic signaling. So stress and stress-related signaling, as we are evolved to deal with, and then the stress and novel challenges that we face today. So we evolved to deal with, being a feast state, then deal with the predator or the acute stress, and then go back to the feast. And now we have this persistent accumulation of everything. So you have chronic social stress, chronic work stress, bad marriages, overfeeding, obesity, underactivity, aging, novel foodstuff, chemicals. Artificial lighting is for the body a chronic stressor. So people, if you put an animal on continuous light, through the day and low light, they become chronically stressed. So this artificial lighting that we have without a very definite, hard, dark period for deep sleep, it constitutes that itself is a stressor. So we have this all, instead of going from one period to another, we have everything happening at once, simultaneously. And then you have this stressful situation here chronically, and the person may have everything at the same time. You may have artificial light, you may be aging, which is a stressor, you may be sedentary, which is also a type of stressor. You can have chronic social stress, chronic work stress, a bad marriage, be overweight, and everything boom, together. And we were not evolutionarily selected for chronic unending stressors. So with chronic stress, you have major depression and stress disorders. Neuroendocrine transduction, you have hormones, cytokines, pyroinflammation, which is very important. It's like a local inflammatory response. And you have endoplasmatic reticulum stress, which actually I wrote a review paper on this. You can look me up and read. So you end up with what I'm calling now, it's a new concept, persistent pathogenic signaling. And the outcome of persistent pathogenic signaling can be depression, obesity, diabetes, cardiovascular disease, cancer, and it could be autoimmune disease as well, many other chronic illnesses. So I'd like to finish this talk by my conclusions, which are that we study, typically when I do research, most of us who are in research, we tend to study one hormone or one behavioral paradigm. So we do stress, or then we don't do stress. We have a control group and have a stress group. The stress group is only stress. The control is not stressed. Then we give one hormone or one substance, and we study things in isolation. But today our bodies are simultaneously flooded with signals. Acute stress that becomes chronic stress and depression. We have excessive food availability, overeating, obesity, and metabolic syndrome. You have sexual arousal, reproduction, and child rearing, which keeps going. And we don't know the effects on the children as they are, still in the uterus, and then in early childhood, what is the impact of all of this on the parents and on them? So the signals no longer alternate. There is no rest. Our body is bombarded with all of the signals all the time. So this represents what I'm calling persistent pathogenic signaling. And we must study, both in animal models and clinically, the effects of these combined signals in our bodies. The elucidation of the mechanisms and pathways of what I'm calling now persistent pathogenic signaling will advance science. But to do that, we need to be able to conduct more complex and sophisticated experiments that we subject animals to multiple things at the same time. And then I know it's difficult to then tease out what's causing what, and you may need to have a lot of different control groups. But if you don't look at these interactions of all these factors, we may not understand chronic disease. And that's my pitch for you, is that to really advance the field of a chronic disease, that essentially all psychiatric disorders are chronic disorders. I don't know any psychiatric disorder that's just acute and then, a few days later you're fine. So once you have major depression, bipolar disorder, schizophrenia, autism, obsessive compulsive, anorexia, you just name a psychiatric disorder, they all tend to be chronic. They can get better, and sometimes they get better, they don't come back, but most times they do come back, and the person is in a chronic state of persistent pathogenic signaling. And we don't know exactly the biology of all of these interactions. And I think that that's what the next step of our research endeavors should be. So I'd like to thank you for your time and your interest, and I apologize that I cannot be there to answer any questions, but you can talk to Professor Lin Lu. He knows how to get in touch with me, and I'd be delighted to maybe develop collaborations with you so that we can study this together. But I really believe I have, 4 decades exactly. I graduated from medical school 40 years ago. And I think that this way that we have of the approach that we have of looking at things in isolation and looking at like one behavioral paradigm, one, knockout, one overexpression, one, we do one thing and then we measure what happened as a result of whatever intervention we did. That's not going to teach us very much, because a patient, a person who has a chronic illness, is subjected to multiple signaling nonstop. And that, in my opinion, is what's making them chronically sick. This kind of lack of rest, like this bombardment of all of the signals simultaneously. And that's not what evolution prepared us for. So anyway, it's been a great pleasure, and I always like to talk to this wonderful audience in China. And I hope that we can travel again at some point soon. And when we can, I will be delighted to go there and meet with you in person. Thank you so much. Good night.